You know what I mean? Just pinging me? It's like my server's pinging me for not going bot, but it's like you're the one out of base that just walked fucking mid for no reason. You know what I mean? My server's not flash autoing the 1 HP fucking Aphelios. And then my my jungler's in the 1 HP. My server's not flash autoing. My server's not flash autoing the 1 HP fucking Aphelios. And then my my jungler says report the fucking mid laner. Yeah, bro. We're not flashing to auto the 1 HP Aphelios to report the mid laner. Oh god. But you know what's so weird? I swear when I have teammates going 0-10, no one says shit to them. But it's like when it's me, I have yoke sitting here spamming this shit. You know, I'm like 99% sure that this Udyr is English, actually. It's like, the more that I read his messages, the more I get like native English speaker vibes. No, this guy's 100% not Korean, I don't think. Dude, what is this guy even typing? Alright, guys. Yo. Hello?
What you wanna talk? Speak.
Dude, why are you so crazy?
What you wanna talking with me?
Bro, okay, well, I mean, you spend the
Bro?
Are you okay?
Yes, I'm okay.
Okay. You spent
What you wanna talking with me?
Okay, I'm trying to tell you.
You want a voice?
Bro, I am trying to tell you.
You want a voice?
Bro, I am trying to tell you.
You want a voice?
Bro, I am trying to tell you, but you're interrupting me.
Okay, go on.
Okay. You spent the whole game insulting me. I was filled, my Galio entered my lane level 2, and then it was unplayable, and my server kept forcing me to lane swap.
I was insulting you.
Yes, you kept calling me a bad dog and telling me that my mom's dead.
Yes.
Okay? So we
What's the
agree.
problem?
Okay, well,
Yes, what's the problem?
I mean, don't you think it's a bit excessive, dude? Like, I'm filled, I didn't say anything against you, and my Galio entered my lane.
Yes, Galio into your lane. Yes, you were 2v1. Got killed.
Yeah,
Isn't
because
it?
he entered the gank. That's how it works.
So what?
What do you
So
mean?
what?
What do you mean, so
Was
what?
that Galio's spot?
Yeah, it was actually.
You wanna say it to me? It was Galio's spot.
Do you want to watch the
Is
replay?
that? Yes, you wanted me to look replay stream?
Dude, okay, bro, listen. I am
saying.
sharing screen on Discord. Do you see the screen on Discord?
Yes.
Okay.
Go on.
Well, I'm trying to. Okay.
Okay. Oh,
Why are you making those sounds?
at the beginning of this game, I was attacked there.
Yeah, you got invaded.
Yes. I wanted you to give me a ice stone in my
What?
F6, in my bird. I signed you so many times, but you ignore it.
Okay.
You can see.
How do you
You
want
can
me to
see.
move
Okay,
without...
no matter. You can. You you want me
Bro, you're
to
literally
see the
hyperventilating because
replay?
you know you're wrong.
What?
Is what I'm saying confusing? You're hyperventilating because you know you're wrong. How do you want Ambessa to move here, bro? Look at this position. Obviously, he's invading you. He has a lane priority. What do you want me to do? I can't even flash over the wall to help you, bro. If I walk here, I die. Do you
Yes,
disagree?
yes. I don't want you come.
But you just told me you did.
Who's that?
Who's what?
I wanted you to give me a ice storm.
An
So many
ice
times I
storm?
signed you. Can't you understand? That depends where I'll go. Is that hard to understand?
Yes, it's
I
very hard to
I
understand.
just need an ice storm.
Do you mean a ward? Like this thing. Wait. This. Ward?
Yes, yes,
Okay, okay,
bird. Yes,
okay,
I want you. I want you to give me an ice storm.
okay. Yes, I could have warded, but we still had a ward, so we knew he was there. Like, it works out fine. Like, what's the problem? You still got the ward, didn't you?
Yes, I still kill their jack.
Yeah,
But
congratulations.
but but I can't promise whether he will come or not.
Okay, so what are you trying to
It,
prove with
it
this?
was a dangerous option.
Dude, what are you saying?
Why are you laughing?
Because what you're saying,
You
it's just
didn't. You
crazy, dude.
didn't help me.
Dude, okay, what you're saying makes no sense. You're talking about dangerous options, and like, dude, what do you mean? Like, what are you even talking about, bro? I don't know what you mean.
You don't know what I mean it?
No, I don't. Like, okay, you needed a ward early, you didn't get the ward. It happens. You still put a ward and you got the kill. Like, what's the problem?
It was just lucky.
Okay, good. Then we
Because
got lucky.
because
Cool.
because he came. It was just lucky. If he came earlier, I will lose much.
Okay, but it's fine, bro. Like, my bad. My bad I didn't
Yes,
put the ward early.
yes,
Okay?
but you didn't. But you
Dylan knows
ignored
farms so
me.
hard every game.
Let's see how many times you pinged for a ward. Okay?
Okay, go.
Let's look.
Yes, yes. You were standing here.
What do you mean?
You were
Yes,
standing
yes!
here. Yes.
Where's your ping? You're saying
you
I'm...
didn't. You didn't. Okay, okay. Standing here is all right.
What's your
You don't know.
point?
You don't know what I am going to do.
No.
No matter. Standing here is all right. You are good meat.
Okay, it's all right. Thanks.
Okay, good meat. All right, good meat.
Okay.
Go on.
Now let's watch.
Okay. Okay, good.
Bro, you did 0 pings for the ice stone. 0 pings.
Yes, you were standing here.
What do you mean?
You were
Yes,
standing
yes.
here.
Where's your ping? You're saying
You did it. You did it. Okay, okay. Standing here is all right.
What's your
You
point?
don't know what I am going to do.
No.
No matter. Standing here is all right. You are good meat.
Okay, it's all right. Thanks.
Okay, good meat. All right, good meat.
Okay.
Go on.
Now let's watch.
Okay. Okay, good.
Bro, you did 0 pings for the ice stone. 0 pings. 0.
0 pings. Go
Ze-
on. Go on. Go
Okay.
on. Okay, go on.
I'm
Do you,
going.
what? Okay, go on. Go on. Go on. Okay, now.
Okay, 1 ping.
Uh, uh, your location. Okay, go on. Go on. Go on.
I'm going.
I want to read you an email that I was asked to keep confidential. I've been thinking about this for a long time, but I now believe that reading it to you will go some way to explain why I'm worried about the status of scientific research generally, but especially in the foundations of physics. I received this email about 7 years ago after I published a comment in Nature Physics titled "Science Needs Reason to be Trusted." In it, I explained how I lost trust in scientific self-correction after I realized how much of what's published in the foundations of physics is nonsense and continues to be nonsense. This email came from someone who I've met a few times but don't know in any depth, and who at the time worked at a top institution in the United States. To honor the request of confidentiality, I've removed some details. Hi Sabine, I'm if you remember me. I'm not using my work email. The topic is a bit delicate and I hope that our conversation will remain confidential. I'm contacting you regarding your recent paper in Nature, which made a lot of noise. First of all, congratulations on a nice paper. If you wanted to attract attention, you managed to do this. Actually, I'd like to ask you next time, think not only about short-term personal benefits, but about the community in general. You understand what consequences your publication might bring for our community? What are all these BSM model builders with exaggerated self-opinion going to do afterwards? What about experimentalists who survive hiding inside big multi-TV collaborations? Can you offer them all any decent employment alternatives? Some of them have families and young children. Some of them are already too old to get employment elsewhere. For some of them, academia is the only way to get US visa. If you like, yes, what we created is a bubble, but it helps thousands of those guys and their families not to die from hunger. We all do the same stuff and have some trade secrets. For example, I'm one of the authors of the so-called model. Pretty useless stuff, old refurbished with a couple of new blows and whistles. But if people buy this and it helps them to get grants, who cares? For people who pay us, all we do is just noise. They have zero idea that elementary particles exist. They pay us from public funds, not from their own, and basically pay for something cool, some new crazy hype, which they need either to include into their science spending reports or in case of universities to attract students. Your paper made a lot of noise and most likely will affect redistribution of HEP funds towards other areas, but I doubt that you'll be able to suggest and implement any organizational changes. Also, any changes of quality criteria which would demonstrate uselessness of somebody's work will have zero chance of approval. I understand that all what I wrote above might sound a bit harsh, sorry for this, but this is how our society is built, and this is not only a problem in the HEP community, but also exists in all other areas. My heart is bleeding when I regularly see bright and intelligent persons with independent ways of thinking leaving academia or getting kicked out, whereas obedient idiots remain. But there's nothing we can do. Those who get kicked out usually find better opportunities outside of academia. Those who remain in academia accept the rules and enjoy the comfort of academic life. Of course, sometimes there are exceptions, like string theorists Smolin and White, but I doubt you'd like to share their destiny. I'm reading this to you as an illustration, a rare example of somebody else's honest words. I can't prove to you that this email is real, so you'll have to take my word for it. In contrast to the person who sent this email, I don't think that taxpayers are stupid. We're not paying physicists for crazy new hype. We want to see results. And soon taxpayers will start asking some tough questions. An example. So they told you that this Dune experiment that's being built from some billions of dollars of public funds at Fermilab will tell us why we exist or why the universe didn't disappear. I regret to inform you that it won't do any such thing. Regardless of what the result of the Dune experiment will be, it'll not tell us why the universe contains more matter than antimatter, because this question is impossible to answer within the context of our current theories. The matter-antimatter symmetry that Dune is supposedly shedding light on is a pseudo-problem. It's a story that physicists have made up that they're now selling to the public, because they think that once they have the money, it doesn't really matter if they deliver what they promised. Though, to be fair, I think that some of them are honestly confused about what CP violation in the neutrino sector even says about antimatter. What will the experiment do? It'll measure some properties of neutrinos. What's that good for? It's good for keeping particle physicists employed, because some of them have families and it'd be unfair if they had to do something useful for their income, wouldn't it? And has anyone even noticed that the US government spent another $2 billion or so on a new particle collider at Brookhaven? Its purpose is to improve measurements of the quark and gluon distribution inside of heavy ions. What's it good for? You're not supposed to ask. You're supposed to believe that you're too stupid to understand what it's good for. But let me fill you in. It's good for keeping particle physicists employed. Meanwhile, the Chinese are laughing their asses off that you think it makes your country worth defending. That particle physicists have created these bubbles of useless research is not a problem that can be fixed from inside the community. The only way to fix the problem is to stop paying them. I'm afraid that this is exactly what's going to happen. I didn't want this to happen. This is why I wrote my 2017 comment. But at this point, it's too late for them to change anything about it. I've read this email dozens of times, and each time I'm stunned by how condescending it is to all the people who do honest work and whose taxes pay for academic jobs. It makes me sick. And it makes me glad that I no longer have anything to do with this so-called research area that's rotten to the core. If you're one of the many physicists who know full well what nonsense research I'm talking about, but you still keep your mouth shut, if you're one of those who laugh about me because no one believes what I'm saying, if you're one of those who spread lies about me, like that story that I was invited to give a talk at CERN but was afraid to go, did you make that up? I hope it was amusing. But Jesus, use your brain. Your problem isn't that I'm making noise. Your problem is that you're lying to the people who pay you. Your problem is that you're cowards without a shred of scientific integrity. Your problem is that every bubble eventually bursts. By the way, the reason I now call it nonsense research and no longer bullshit research is that YouTube flags the letter as profanity, and we don't want to be profane on this channel. That would be absolutely terrible. All right, let me know what you think about all this in the comments. There are many reasons why you might not want other people to get your private information, and yes, I have reasons. This is why I signed up to Incogni, who've been sponsoring this video. You see, each time
Okay, then you ping missing.
Yes, your location. It was that hard?
But then we
Was that
saw
very hard?
Karthus there. I'm going. Okay, then you ping missing.
Yes, your location. It was that hard?
But then we
Was that
saw
very hard?
Karthus there.
This is my ice stone.
No, it's mine.
What? What? Your ice stone?
Yes, dude, literally. At 45 seconds, I ran there and I put it level 1.
What? Was that your ice stone? That was my ice stone. You have ice stone too. You ignored me. And 2v1 got killed.
Bro, look,
Yes, yes.
you don't have
Yeah.
an ice stone. This one was
Yeah.
literally mine.
Yes, this is my ice stone. So
No,
that I
it's
have
mine.
no ice
Look,
stone.
look, look,
Bruh.
look at my screen. You see this?
Oh.
It's my
Yes,
ice
yes,
stone.
this is,
It's there.
that means you have ice stone.
No, it
Okay?
doesn't, bro. No, it doesn't.
Oh my god. Why we are confusing with these why we are confusing with these? That means I have no ice stone. I have put it in there. Can you understand? You have ice stone.
I mean, dude,
That
I
was
just
my
don't
ice stone.
agree. I just don't agree. I just don't agree.
That was my ice stone,
It
bro.
wasn't.
You ignored me. You
Okay,
helped me
listen.
nothing.
I placed the
Okay,
ward here
okay.
level 1, and then afterwards, I need you to see what happens when the Galio gangs mid. Okay?
Oh, yes, yes. You wanna. I know you wanna talk to me. That it was Galio's fault. That makes you got killed. I can help you, but you ignored me. That makes me very dangerous. I have to do dangerous option.
Okay,
Lose my resource.
bro, listen. I main jungle. Can I just tell you something honestly right now? There is no danger because the fact that there's a ward here and we saw Karthus
Yes,
on the ward
yes,
here.
yes. I know.
If we listen, if we don't see Karthus here, then we know he's in your bot side. And if we do, right? If we see him here, then you're good. Like either way, you either just split the map or you see which you saw that he's gonna be here and then you can just kill him. There's literally no problem.
Yes.
This ward gives you all the
You
information.
okay, but you yeah,
It's no danger.
not me. It
Hey,
means
listen.
nothing. It
I
was
just
my I have put it in there. Can you understand? You have ice stone.
I mean, dude,
That
I
was
just
my
don't
ice stone.
agree. I just don't agree. I just don't agree.
That was my ice stone,
It
bro.
wasn't.
You ignored me. You
Just don't agree.
have ice stone.
I mean, dude,
That
I
was
just
my
don't
ice stone.
agree. I just don't agree. I just don't agree.
That was my ice stone,
It
bro.
wasn't.
You ignored me. You
Okay,
helped me
listen.
nothing.
I placed the
Okay,
ward here
okay.
level 1, and then afterwards, I need you to see what happens when the Galio gangs mid. Okay?
Oh, yes, yes. You wanna. I know you wanna talk to me. That it was Galio's fault. That makes you got killed. I can help you, but you ignored me. That makes me very dangerous. I have to do dangerous option.
Okay,
Lose my resource.
bro, listen. I main jungle. Can I just tell you something honestly right now? There is no danger because the fact that there's a ward here and we saw there is no danger because the fact that there's a ward here and we saw Karthus
Yes,
on the ward
yes,
here.
yes. I know.
If we listen, if we don't see Karthus here, then we know he's in your bot side. And if we do, right? If we see him here, then you're good. Like either way, you either just split the map or you see which you saw that he's gonna be here and then you can just kill him. There's literally no problem.
yes.
This ward gives you all the information.
Okay, but you don't know jungle.
What?
If they draft first cleared his blue buff and then attacked my bird and then my red buff. It it makes sense, you know? It makes sense.
Dude, it doesn't matter. Like, if he takes your entire bot side or all this or anything, it doesn't matter. Like, you can just play
I
for
don't waste
split
my
map.
time.
Entire bot side or all this or anything, it doesn't matter. Like, you can just play
I
for
don't waste
split
my
map.
time. I don't waste my time to
Then
catch
don't go
him.
bot side, go top side. What's the problem? You do know that on this board when you saw he only had red. He's not gonna, or he only had blue. He's not gonna fucking go blue Raptors, fucking Raptors. No one does that.
I think it is hard to talk with you with this. Really hard. Maybe you you didn't play jungle for times. Okay, that's
Okay,
okay. Okay, go on. See what Galio do.
okay, let's watch what Galio does. Are you ready?
Yes, yes.
Keep in mind, you still haven't placed your ward yet. I'm the
me you you can clear this soldier?
Yes, I have W.
Okay, that's okay. Their mate going to LV4. You have only 100.
Yes.
Yes, you you will not die.
I don't think so. I have my W.
Okay. Or
But
Galil's fault, okay?
okay, look. The
Your
problem
your
here.
Hello wonderful person, this is Anton, and today we're going to discuss another fascinating discovery from right here in the Milky Way galaxy, another record holder, but specifically what seems to be the most massive binary star system ever seen, at least within our own galaxy. But in this case, a star system that's also kind of bizarre and doesn't actually make a lot of sense. And so let's discuss this discovery and also briefly talk about some other massive stars already known to us. With all of this based on a recent study from the research team you see right here that used both archival footage and new observations, mostly using the Hubble Space Telescope, in order to precisely measure the properties of a binary system known as NGC 3603A1, and confirming that the system represents one of the most massive binary systems ever discovered, way bigger than we thought. And so I guess let's start with the exact properties. First of all, this is not close to us, 22,000 light years away, and it's inside a very vibrant starburst region referred to as NGC 3603, the beautiful star-forming region in the southern Milky Way that's known for a lot of massive young stars. And so this is an active cosmic factory producing huge amounts of stars. And this is also the most massive visible cloud of gas in the entire galaxy, potentially making this the most active region in the Milky Way, possibly producing the most stars. But this is also one of the closest such regions to planet Earth, making this extremely important for astronomy because it obviously teaches us quite a lot about star formation, and quite a few really massive, very active stars have already been discovered, with a lot of these stars being very massive Wolf-Rayet stars, responsible for very bright, very massive emissions, and huge amounts of gas and dust released at all times. And some of these stars are super bright, millions of times brighter than the sun, and there's actually quite a lot of them in this region, but at least one of the objects here kind of stood out. You can sort of see it right here. And at first it was believed to be just a single star referred to as HD 97950, but it turned out to be at least 3 different stars, with one of these objects being the pair we're discussing today. And so here we have 2 stellar titans. The primary star is approximately 93.3 solar masses, and its companion is 70.4 solar masses. So this whole system is over 163 solar masses in total, which if compared to some of the other most massive stars discovered to date, would make it like number 5 or so, but number 1 in the Milky Way. And that's because most of the massive stars known to us are all basically right here, the Tarantula Nebula. The large concentration of stars in the nearby Large Magellanic Cloud that contains some of the biggest record holders and some of the most massive, brightest, and most active stars ever discovered. And all of the stars in the Tarantula Nebula and this newly discovered binary are not just large stars, they're essentially at what seems to be the practical limit of stellar masses. Or just to rephrase this, astronomers don't think stars can even get more massive than this. But what makes this system truly extraordinary is also the orbit of the stars. The orbital period of these 2 bizarre giants is just 3.2 days, which was recently confirmed in a study description. And so this very close proximity and this enormous gravitational pull potentially creates very dynamic and very complex relationship between these 2 objects. But this discovery and the analysis was relatively complex. It involved years of careful work and the observations of NGC 3603 star cluster, which by itself is already pretty challenging, mostly because many stars here seem to be concentrated in a very small region. And all of this required exceptional clarity from the Hubble Space Telescope. But the breakthrough came in 2020 when during the COVID lockdown, the undergraduate student Sarah Bodansky remotely used one of the observatories to look through some of the older Hubble data and accidentally discovered something we've never seen before. She noticed that a lot of spectral features doubled when the stars had their greatest motion towards or away from us, which revealed that this was a binary system and not just a single fuzzy star. And specifically, she was able to identify that certain Balmer lines or certain hydrogen lines were clearly doubled and were clearly separated as if there was a certain orbital phase, which allowed the researchers to determine the exact radial velocity even though it was disturbed by various stellar winds. And this led to very precise orbital parameters and the very precise mass measurements. And so by measuring radial velocity of both components and also determining the orbital inclination, by using Kepler's laws of planetary motion, we can then directly calculate the mass of stars. But it's also important to note that these extremely massive stars are actually super rare. And their study usually involves looking at very distant and very crowded regions, such as the previously mentioned Tarantula Nebula. But based on a lot of previous discoveries, now researchers are pretty certain that for some reason, most of these massive stars, or basically over 70% of them, seem to always come as a binary, and they always undergo significant interaction during their lifetimes that then play a huge role in the evolution of stars, evolution of everything around them, and the ultimate fate of the cluster and any other stars in the vicinity. And specifically, these very massive binary systems very often also serve as progenitors of very powerful supernova and binary black holes, which eventually results in the gravitational wave detections we've been detecting since 2015. And so here we get at least one chance to potentially predict what kind of a system this is going to create in the next million years. But the weirdness of the system doesn't end there. Here, the most massive star, the one that's 93.3 solar masses, is currently filling its Roche surface. Or just to rephrase this, its outer layers are currently being gravitationally stripped away and transferred to the companion, the smaller secondary star, with this kind of a mass transfer being a very critical process in the binary stellar evolution. As a matter of fact, at some point, they might even form what's known as the contact binary, where both stars sort of kiss and touch each other. But this, of course, has a lot of effect on the secondary star as well. The secondary star with the 70.4 solar masses has now been observed to be spinning much faster than its synchronous orbital speed. Here it seems to be spinning at 520 km per second, which is something like 40% of its theoretical breakup velocity. In other words, if it starts spinning even faster, it's at some point going to start falling apart. And this rapid rotation is a strong indicator that the secondary has now been spun up by consuming a lot of mass and angular momentum from the much larger companion, essentially confirming that the larger star is feeding the smaller one. But here even the classification of these stars is also kind of strange. They're now identified as O2WN/stars, indicating that despite being somewhat young and somewhat unevolved, their extreme luminosity is pushing them close to the absolute luminosity limit. The limit where the luminosity becomes so powerful and so bright that the radiation pressure generated by nuclear fusion starts to exceed gravitational pull, or basically the star becomes so bright that the light starts to push everything away from it, with the gravity unable to hold it anymore. And this usually leads to the formation of very dense, optically thick stellar winds that then produce very beautiful nebula, such as the ones seen around Wolf-Rayet stars. But in this case, it's just a case of very young stars appearing much more evolved than they should be. And all this just a result of this extreme interaction and extreme activity. But the strangeness of these stars doesn't end there. We also have something unexplained about the temperatures. For some reason, the secondary star is about 5,000 Kelvin hotter than the much more massive primary star. Here, the smaller star is 42,000, the bigger star is 37,000 Kelvin. And this is also maybe the result of the accretion, or basically the star eating the mass from the other star, which seems to have changed the thermal equilibrium, and that also seems to cause the larger star to now evolve much faster than it would otherwise, cooling down much faster than it should. But how exactly does the star compare to some of the other giant stars? Well, right now in the Milky Way, this is literally the record holder, with maybe one other system, WR21a, located in the Carina Nebula, known to have a somewhat similar primary star with 93.2 solar masses. But in essence, there are only like 4 such stars known to us in the entire Milky Way. And though I guess the most famous is Eta Carina, the one that produced the infamous Homunculus Nebula, Even here, the star system is a little bit smaller. Its mass is very likely much lower, but it's also currently impossible to measure because of this enormous eruption in the mid-19th century. This is of course the famous Great Eruption that you can learn more about in one of the videos in the description. But when it comes to other star systems in the nearby Tarantula Nebula, there seem to be some stars that are even more massive, with the most famous one, R136A1, once again you can learn about this in the description below, possibly having a total mass of nearly 290 solar masses based on several observations. But here we don't actually know if this is a single star or a star system containing multiple stars, mostly because this is pretty far away from us in the Large Magellanic Cloud. Although interestingly, one of the recent studies confirmed that most of this mass is eventually going to be lost through enormous stellar emissions over the next million years. And so even though these stars start with hundreds of solar masses, they'll eventually lose possibly up to half of this, creating a massive nebula around the system. And so here, by studying some of the more nearby such systems, such as NGC 3603A1 we're discussing today, it provides astronomers with a very unique opportunity to test ideas and various theories, and to try to explain how stars evolve, how these massive giants affect various stars in the vicinity, and how all of this mass loss eventually results in the formation of stellar dust. Because as we know today, most of this dust actually produces organic molecules, and a lot of this potentially ends up in various planets. And so in some sense, these really massive, really bright stars serve as a kind of a precursor to a lot of complex stellar systems, including systems with terrestrial planets. And so the influence of these stars and their incredibly powerful interactions goes way beyond just a simple interaction, and actually ends up enriching the entire region around them with many very complex elements, potentially serving as building blocks of life. And that's because the stellar wind from these stars ends up producing a lot of organic molecules, with this study revealing phenomena like rapid rotation and very specific spectral characteristics that seem to arise from very close interactions of very massive stars. But I'm sure in the next few months, as the star is explored even more, we'll probably discover something else, which means that we'll come back and discuss this more in some of the future videos. And until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access and a few more things. Alternatively, you can also buy the Wonderful Person t-shirt in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye. Hello wonderful person, this is Anton, and today we're going to discuss some of the recent updates about the most catastrophic event that happened to planet Earth, the idea known as the giant impact hypothesis. The event that represented one of the most destructive collisions in the history of the solar system, that eventually led to the formation of modern Earth and, of course, our Moon. And for decades, the primary question surrounding this event was mostly focusing on the lunar formation and on various unusual similarities between Earth and the Moon. And although some studies that we discussed previously, that you can also find in the description, potentially questioned this event, basically suggesting that maybe it was something entirely different, at the moment most scientists seem to agree that something catastrophic indeed happened 4.4 billion years ago, because otherwise it's very difficult to explain the formation of the Moon. But today we're going to discuss this somewhat recent research that suggests the collision between the hypothetical planet Theia and early Earth might have been far more significant than just giving us the Moon. It might have been responsible for basically forming early life. And so let's discuss this idea and this study in a bit more detail, but here I guess let's start with the very brief history of early Earth. And here we have to rewind time by approximately 4.5 billion years. The early solar system was a very chaotic place. Planets were still forming, a lot of things were still colliding, and quite a few planets, including potentially some of the biggest planets, Jupiter, Saturn, Uranus, and Neptune, all seem to have experienced major collisions. And some of these early planets potentially shared very similar orbits, possibly even getting stuck in somewhat prominent positions such as Lagrange points, which do allow certain objects to share the same orbital parameters. And so the hypothesis here was that at least one of these objects was maybe somewhat similar in size to Mars, but it was also sharing orbit with planet Earth. But because there was so much interaction in the solar system, at some point this object got dislodged. And this object, referred to as Theia, eventually collided with early Earth, with the immense energy from the impact ejecting a vast amount of debris into the orbit around the planet, which eventually coalesced to form the Moon. And so this particular formation hypothesis has been studied for many decades and right now does seem to make a lot of sense. But this collision might have actually had a much more profound consequence for our planet. Because according to quite a few cosmochemical studies, or essentially studies on the chemistry of various planetary objects, Earth as we know it today seems to have accreted approximately 5 to 10% of its entire mass from something known as carbonaceous materials, also known as CCs, which usually refers to any substance rich in carbon, such as for example organic compounds like graphite, or a lot of stuff we find inside asteroids and meteorites. And these meteorites are usually referred to as carbonaceous chondrites. Any meteorite containing a lot of these chunks and a lot of these volatile chemicals, mostly composed of hydrogen and carbon, that can then easily vaporize, but most importantly, is basically essential for life. But there's a bit of a problem. Based on what we know about the planet, Earth seems to have formed much closer to the Sun. And temperatures near the Sun, even back in the days, were much too high for these volatile materials to condense and become part of these early rocky planets. Or just to rephrase this, we don't really expect so many volatiles and so many carbonaceous materials to be present around planet Earth. And that means that early Earth might have been quite dry and quite barren, not so different from planets like, for example, Mercury. So it would most likely be some kind of a wasteland, completely incapable of supporting life. And that's where this Theia hypothesis steps in, because it might have been a massive delivery truck. This new study published in Science Advances by Pascal Courtache and his partner Klaus Mesger strongly suggests that Theia originated much farther in the solar system, in a location where a lot of volatiles very likely existed. And when this volatile-rich Theia collided with proto-Earth, it didn't just create the Moon, it also delivered a lot of these essential ingredients directly to our planet. And in this case, researchers used a very specific chemical model, mostly focusing on different isotopes, for example manganese and chromium. And this allowed them to precisely track the first few millions of years of Earth's formation and understand the chemical makeup of a lot of the building blocks, with findings indicating that early Earth, and very likely a lot of other rocky planets like Mars, Mercury, and Venus, dramatically changed their composition in the first 3 million years, mostly because of a lot of dust and gas being delivered to their surface. But following this initial period, the process of getting new matter mostly stopped, with the result being, well, what we see right now around other planets. Planets closer to the Sun, so Mercury and Venus, were depleted in volatile elements, whereas planets like Mars potentially had some elements, but eventually lost them due to the lack of mass. But Earth does contain a lot of volatiles, so they must have come from something else. In this case, Theia seems to make the most sense. And here, this object was very likely some kind of a small stony planet, but enriched in carbon and organic compounds, with all these compounds suddenly delivered to the Earth's surface. But interestingly, this is just one of 2 studies released very recently that kind of implies something very similar. There's actually another study you see right here by Branco, Mercado, and Raymond that suggests Theia didn't just bring volatiles, it also very likely delivered a lot of water. And this is a puzzle for geologists because water is generally much less dense, meaning that in theory it should rise to the crust or the oceans. But here the simulations from the study suggest that Theia delivered all of this water, mostly into the Earth's mantle, and there hasn't been enough time for most of it to reach the surface yet. And so deep inside our planet there is very likely a lot of leftover water, representing a direct legacy of this enormous impact, with both studies providing validation for cosmochemical studies, explaining how Earth acquired significant fraction of carbonaceous material and a huge amount of water on top of this, with these 2 propositions explaining and solving quite a lot of unusual mysteries. For example, previous chemical studies on Earth and Mars show that in case of our planet, it seems to have 10 to 15% carbonaceous material, while our red neighbor, Mars, seems to just have a few percent or just a fraction of the material. And that doesn't really make sense because Mars is much farther from the Sun, so technically it should contain more. And so if carbonaceous material in the inner solar system was mainly in the form of these large planetary embryos that would then collide with various objects, it would be much easier to explain why some planets seem to have this misbalance. Here Earth would receive a huge dose, while Mars potentially only experienced much smaller collisions, and thus much less delivery of various volatiles. And so here this particular model actually questions the origin of Theia. It was unlikely to have come from the same orbital parameter as Earth, and was extremely more likely to be some kind of a volatile rich body coming from the outer solar system, possibly even beyond the asteroid belt and beyond Jupiter. And here the simulations also suggest that it was really Jupiter and Saturn that mostly scattered a lot of these materials early on, very likely causing most of these collisions. But I guess the main question here is, so why is this important and why does this matter? Well, in this case, the implications are quite vast and do extend way beyond our planet. Because obviously in this case, Earth is also the only planet where life has been officially confirmed and also directly depends on these two things Theia brought to Earth: organic molecules and carbonaceous materials and a lot of water. And so one of the potential implications here is of course in regards to the origins of life. Maybe life requires these dramatic events, and actually very specific events, very likely involving giant volatile rich impactors from the outer star system, to suddenly receive a lot of essential building blocks for life, and potentially a lot of other stuff, in order to kickstart early formation of life on the planet. Which also potentially suggests that life in the universe is maybe not so common after all. And so even though today most researchers focus on Earth-like worlds when trying to discover some kind of a habitable planet out there, the conclusions from these two studies suggest that we're still just going to find some kind of a barren rock unlikely to support any life at all. And it's really only certain rocks that experience these Theia-like impacts that then maybe have a chance for life to finally form. But even in this case would still require quite a specific balance and quite a few critical things to happen at the right time. And so far these two studies put a strong emphasis on these moon-forming impacts as not just being geological events, but also being biologically foundational, at least for the history of our own planet. And although there were some limitations in the study, such as not accounting for all of the complex dynamics in the early gas disk, the research still provides powerful dynamical validation for most chemical studies involving planets and offers us a plausible scenario for how Earth became a unique life-supporting planet. Which in summary means that the story of Theia is no longer just about the moon, it's now about the life itself. This event potentially led to the emergence of life that then physically transformed the planet into the Earth we see today, making this a stark reminder that sometimes our existence might just be the result of very precise and even somewhat lucky events that may not be very common out there. But once again, this is, at least for now, still a hypothesis. And if you disagree, let me know why in the comments below. But we'll definitely come back and discuss this more in some of the future videos because this is probably one of the most fascinating topics when it comes to the formation of Earth and the Moon. And so until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads, and can DM me directly, or by joining a general membership that grants you early access and a few more things. Alternatively, you can also buy the Wonderful Person t-shirt in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.
I know what you mean. Look, that that game, dude. My sibber tells me go bot. She tells me go mid. She
Uh,
tells me go fuck myself. Like
I,
I,
I, I, I really don't want to talk to you more.
dude, please.
I found that many Korean always think this is others' fault. This is others' fault. Never find self.
Go fuck myself. Like
I, 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 I really don't want to talk to you more.
dude, please.
I found that many Korean always think this is I,
Dude, my fucking sibber was throwing me around.
and all Galio's fault. Okay.
dude, dude, my fucking sibber was throwing me around that game like I was a dirty dude in the fucking medieval ages. Do you understand that?
I don't.
I know what you mean. Look, that game, dude. My sibber tells me go bot. She tells me go mid. She
Uh,
tells me go fuck
uh,
myself. Like
I, 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 I really don't want to talk to you more.
dude, please.
I found that many Korean always think this is others' fault. This is others' fault. Never find selfish.
Okay, listen. Poo,
Okay.
poo.
I don't want to
Listen.
talk.
Wait. Last thing. Last thing. My Galio can help me push out the soldiers here. He decides instead that when Set is having all of his cooldowns up,
Thank you to Delete Me. Thank you to Delete Me for their support of PBS. One of the most important reasons we go to space is to know our own planet better. Today, I'm going to tell you about an orbiting facility that literally watches Earth's cities and biosphere breathe and grow and die with incredible resolution. I'll talk about its profound existential and economic importance and why it's in danger of being lost. Hey everyone, before we get started, I wanted to let you know that August 8th was the 94th birthday of Sir Roger Penrose. The work of Sir Roger and his famous Penrose diagram have been an important part of space-time, and to celebrate, we have a limited edition Penrose diagram pin. This pin is based off our original design for the Penrose diagram. The pin will only be available via pre-sale through mid-September. We're also offering 10% off for the first 24 hours, as well as 5% off all Penrose-inspired merch. There are links to the merch store in the description. Now, on to the episode. Look again at that dot. That's here. That's home. That's us. In 1990, Carl Sagan asked NASA to turn the Voyager 1 spacecraft around for one last snapshot of its planet of origin before it began its long, cold journey towards interstellar space. The result was this image, dubbed the pale blue dot. And if you haven't heard Sagan's full speech and want some existential shivers, there's a link in the description. We normally think of astrophysics as an outward-looking science, but one of the most important reasons to look outwards is to better understand ourselves. And one of the most important reasons to build telescopes in space is to keep a careful eye on the most precious planet in the universe, our own Earth. Historically, a lot of this good work has fallen to NASA because no one else has the same level of joint expertise and experience in both rocket science and planetary science. One of NASA's Earth-watching programs is the Orbiting Carbon Observatory, the OCO program, which is dedicated to high-sensitivity, high-resolution observations of atmospheric carbon dioxide. The program stumbled at first. OCO-1 never quite made it to orbit after its launch vehicle fairing failed to separate. That was in 2009. OCO-2 launched successfully in 2014, and with the spare parts from both 1 and 2, NASA managed to assemble a third instrument, OCO-3, which now resides on the International Space Station. In fact, OCO-3 wouldn't exist if OCO-1 hadn't failed, so silver lining? From now on, if I'm referring to both OCO-2 and 3, I'll just say OCO. Despite the rocky start, OCO is performing quite a bit better than expected. In fact, it has a pretty remarkable ability that wasn't even planned, and I'll come back to that. But first, the specs. OCO-2 is part of the A-Train, a close-flying chain of Earth-observing satellites. This satellite constellation flies a near-polar 100-ish minute orbit at around 700 kilometers. The orbit is sun-synchronous, which means the path maintains its orientation relative to the Sun, and that helps with the consistency of OCO-2's measurements. OCO-3, being on the International Space Station, has a lower, faster orbit. Together, the OCOs produce high-resolution maps of CO2 density across the planet. So, how do they do this? When sunlight passes through the atmosphere, reflects off the surface, and then passes back through the atmosphere, each type of molecule absorbs a particular set of wavelengths, revealing absorption lines. We see a sort of barcode when that light is broken into a spectrum. OCO captures the spectrum around 2 of the infrared CO2 and around 1 of the oxygen lines. The depth of the lines is sensitive to the number of molecules, while the line widths carries information about pressure and temperature. The oxygen line is useful for things like path length and geometry. With these data, the OCO pipeline applies sophisticated physics like radiative transfer models to solve an inverse problem, asking the question, what CO2 profile best explains these spectra given the viewing geometry? The result is a stunningly precise average density of CO2 along the column of each observation. These measurements allow OCO to map CO2 column density with a spatial resolution of a few kilometers and a sensitivity of around a part per million. This reveals the sources and sinks of atmospheric carbon down to neighbourhood level precision, and it does this frequently enough to see seasonal swings and year-to-year anomalies. Combined with other atmospheric data, OCIO's observations are used to build highly detailed models of the circulation of CO2 around the globe. This is important for knowing not just where CO2 is being produced, but also where it ends up. When OCIO-2 launched, it executed its intended functions exactly as planned, and then it revealed an ability that no one expected. It could literally see plants breathing, the faint glow emitted by plants during photosynthesis. When chlorophyll is energized by incoming light, most of it goes to fueling the plant, but some of that energy is quickly re-emitted as infrared light. Now, sunlight that is simply reflected off the Earth's surface retains the dark absorption lines of the incoming sunlight, but this photosynthetic glow partially fills in those dark bands, allowing OCIO to measure this solar-induced fluorescence. In this way, we can now measure when and how efficiently plants are breathing. This has broad and incredibly powerful applications. Combined with other data, OCIO allows us to watch the natural daily and seasonal shifts in plant metabolism across the globe. It also allows us to monitor the health of critical photosynthesizing systems, from forests to savannas to ocean algae and agriculture. For example, OCIO facilitates the prediction and assessment of oncoming droughts in a way that was previously impossible. A plant's photosynthesis efficiency drops very quickly in response to stress, for example due to the heat and dryness that precedes a drought. And these changes happen before there's any visible change in the plant life. Because OCIO can monitor photosynthesis, it can track how vegetation is responding to harsh conditions. In fact, it's that response of vegetation that often worsens and even causes the drought. So, when temperatures rise before a drought, plants actually become more productive and in the process draw water down into the ground. When temperatures then spike, soil moisture has become dangerously low, leading to the onset of flash drought in mere days. SIF monitoring is our best tool for catching this dangerous cycle before it happens. And it's not just security from catastrophic crop failure. OCIO also enables us to perform highly nuanced measurements of plant metabolism, which lets us assess stress, forecast growth, and generally do global vegetation health monitoring. Arguably, the most important application of this is in crop yields. OCIO's SIF data has been used to predict US Corn Belt crop yields down to the county level. It can do this with better accuracy than current USDA methods, and also much sooner. It's actually hard to overstate the importance of this. Besides the obvious fact that we have a lot of people to feed, agriculture is an enormous part of the economy. In the US, agriculture and its dependent industries represent several $100 billion to $1.5 trillion in economic activity, depending on how you count, and also employs tens of millions of people. More reliable crop yield predictions is ultimately important for everyone, and this benefit is very much weighted to rural communities, and farmers in particular. For example, they often rely on futures contracts, payments based on crop yield predictions to finance their efforts. Better yield predictions means better financial security for farmers and better food security for everyone. Now, a primary goal of the OCIO program was to track CO2 for the purpose of climate change modelling and mitigation. However, the program is, and always was, way broader than this, and would be a no-brainer even without the climate factor. OCIO can pinpoint carbon sources and plant metabolic activity, which can be a powerful strategic tool both for geopolitical and humanitarian reasons. For example, it enables us to keep track of carbon-intensive activity like urban or industrial development, whether of friends or rivals. With remarkable resolution, it would literally be able to see a single new power plant or large factory, no matter how well it was hidden from our regular cameras in the sky. OCIO also monitors changes in global crop health, enabling prediction of crop failure and the potential resulting famines and refugee crises. Regardless of what you think we should do about such things, it's always better to know in advance. And heaven forbid a major conflict breaks out between world powers, but if that happens, it seems prudent to retain the ability to sense new industrial build-up, shifts in land use, supply chains, etc., efforts that might otherwise be screened from direct observation. It's amazing that we have this capability at all. Currently, both OCO2 and 3 are in perfect working order and could run well into the 2030s and further. They were a substantial investment to build at around $750 million. However, the ongoing cost is relatively cheap, with a combined budget of $16.4 million proposed for this year. That's a tiny fraction of the potential returns for their benefit to agriculture alone, to say nothing of the much larger cost-risk analysis against existential concerns like environmental and food security, and even defense concerns. Let me reiterate, no nation other than the US, nor private organizations, have anything approaching the capabilities of the OCO program. Nonetheless, OCO was zeroed out in the White House's budget request for NASA this year, 2025. NASA's OCO team has been directed to plan for a mission closeout that means switching off OCO3 and deorbiting OCO2, burning it up in the atmosphere. This still needs to be approved by Congress, so it's not quite a done deal, but there's a fair chance that all of these amazing capabilities you just learned about will literally go up in flames. It's not too late, but it will be soon. Now, it is possible to build and launch new facilities. There was a plan to build GeoCarb, a satellite with expanded sensitivities to sit in geostationary orbit over the Americas. It would have been a great complement to OCO because it would increase the resolution in NASA's home continent while OCO continues its global surveillance. The project was cancelled due to cost overruns, so currently there are no plans for new OCO-like facilities. If we ever do replace OCO, we'd be much better off replacing it while OCO is still running. The program now has a decade-long baseline of global monitoring. Shutting that down means breaking a continuous time series that future satellites will need for cross-calibration and continuity. From a data analyst perspective, that cross-calibration is incredibly important, to say nothing of the importance of continuity from a security perspective. Look, of course, hard decisions need to be made when balancing a budget, but those decisions also need some economic foresight, and the potential value of OCO can't be overstated, even if we only care about the economic return. Sagan usually says it best: our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. NASA's oft-stated prime directive is to explore the unknown in air and space, innovate for the benefit of humanity, and inspire the world through discovery. The image of the Earth as a lonely blue speck, barely a pixel across, surrounded by the vast emptiness of space, certainly does that. So does OCO's exquisitely resolved surveillance of a living, breathing planetary biosphere, our only known refuge in a vast and inhospitable space-time. Thank you to DeleteMe for supporting PBS. DeleteMe helps protect you from more than 800 data brokers. Data brokers are companies that scrape public records, mine social media, and buy commercial data to build and sell detailed profiles, often without individuals ever knowing. How does it work? Well, the platform searches through hundreds of data broker sites, identifies where your information is exposed, and issues official removal requests. But they don't just remove your information once. DeleteMe keeps monitoring, so if a site tries to slip your details back online, they'll work to remove it again. You'll also get regular privacy reports showing exactly where your info was found and removed, plus a dashboard for
In the last couple of years, one of the most incredible discoveries coming out of James Webb Space Telescope was essentially this: a collection of very strange, very distant objects that seemed to exist in the universe when it was only about 300 million years old, or even younger. Strange red objects representing some of the most distant objects we have ever seen. And that's because a lot of these objects are extremely redshifted and are only visible in the infrared light, which is of course what the James Webb was built to see. But so far, most studies assume that these were basically baby galaxies, or essentially proto-galaxies, or maybe massive early star clusters that seem to have formed in an extremely early universe. Except that in April of 2023, we've discussed a really interesting alternative explanation. Maybe, at least some of these objects, especially the ones that appear to be very compact, and the ones resembling a point source, could only be explained if these were actually very exotic dark stars. A concept we've discussed previously, but a concept that I wanted to briefly discuss once again, just so that all of this makes sense. And that's because extremely recently, Catherine Fries and the team you see right here released an additional study that actually provides even more evidence that maybe this is something super exotic. And so let's talk about the study and the explanation in a bit more detail and discuss if this is indeed supermassive dark star candidates. But first, briefly about the idea of dark stars. Now, historically, this concept of dark stars has been proposed a long time ago. As a matter of fact, as far back as 1783, when early astronomy was still being developed. The original dark star concept was by John Michell, who discussed this concept with Henry Cavendish, and then published this in a letter to the Royal Society in 1784. That's literally 250 years ago. But here he was talking about dark stars that would be actually kind of similar to black holes. Stars so large and so massive that they would basically trap all light because of the surface escape velocity. And while based on modern theories, we know that something like this would most likely just become a black hole. But over the years, scientists have also developed a separate idea once researchers realized that there seems to be a lot of additional stuff in the universe that we could not explain. For example, dark matter. And so the explanations for dark matter that essentially involve some kind of a particle suggested that sometimes some of this dark matter can become extremely dense and collapse into some kind of a cloud-like object that starts to attract a lot of hydrogen and a lot of helium. In essence, this is actually how today we explain the existence for various galaxies. As a lot of dark matter accumulated into larger and larger chunks, it started to attract hydrogen and helium that eventually started to coalesce into larger objects, formed some of the first star clusters, and basically created early galaxies. But in some rare cases, some of these dark matter particles might also create their own individual objects, with even a little bit of dark matter potentially creating large enough clouds of hydrogen and helium that they start to form individual, massive, compact objects. And though in a typical star, normally the energy is produced as a result of fusion, which is when hydrogen combines into helium and releases energy, inside of these bizarre dark matter objects, they start to be powered by something entirely different. Tiny dark matter particles start to bump into each other, start to annihilate, and essentially result in the production of energy as well, releasing a tremendous amount of heat that then starts to heat up hydrogen and helium inside the cloud. And so this is what a lot of dark matter researchers refer to as dark matter stars or dark stars. These would be enormous clouds of hydrogen and helium as large as 1,000 astronomical units across, or essentially 50 times as large as the orbit of Pluto, that because of this dark matter annihilation produce extremely hot objects with the surface temperature for this hydrogen reaching 10,000 Kelvin, kind of resembling these very massive O-type stars, but also very massive overall, over 100 solar masses in mass. And as these objects accumulate more and more mass, they do start to grow larger and larger, but at some point, once a lot of dark matter has been annihilated, and these stars no longer produce enough heat and enough energy to sustain themselves, they potentially suddenly collapse, resulting in a very massive, dense object. And with some of the most massive clouds, potentially thousands or even millions of solar masses, we get a supermassive black hole. And so some of these objects that can become very large and very massive eventually result in extremely massive central black holes, around which we expect a galaxy to form. And so this is actually one of the potential explanations for the existence of supermassive black holes, especially the ones too massive to exist. But naturally, this was just a hypothesis and just one of the explanations. We didn't really have any evidence. As a matter of fact, up until James Webb, there's only been some circumstantial evidence of dark matter stars, and mostly based on observations of gravitational waves and potential collisions of smaller objects. Yet, as I mentioned, in 2023, at least one study that you can learn more about in one of the videos in the description suggested that some of the observations from the James Webb were actually consistent with being point source dark matter stars, because it's the only way we could explain their brightness, the only way we could explain why they existed so early on, and of course explain why they were so tiny and appeared star-like, with the initial spectral analysis of some of these objects suggesting they were between 500,000 and 1 million solar masses, with luminosity of billions of suns and a radius of at least 10,000 stars, which is of course much larger than any star in the modern universe. And though some studies propose that these are just very unusual BB galaxies, or maybe even giant black holes covered by a lot of dust, these explanations sort of created even more mysteries. If these were giant black holes, how exactly did they form so early? And if these were active stars, once again, why did they form so early? And why there's so many of them in such a small space? So basically here, no matter what explanation scientists proposed, there was always something that was missing. However, the dark matter star hypothesis originally suggested that such objects could actually exist as early as 200 million years following the Big Bang. So basically these dark matter stars could easily exist in the early universe and would mostly be made out of hydrogen and helium, orbiting around a central point made up out of a lot of dark matter particles. But following this initial proposition in 2023, we didn't really have any new updates or any new suggestions, and that's until now. In this recent paper, researchers looked at some of these objects even closer, but this time decided to focus on something else. They used the James Webb's ability to analyze colors of light, here we're talking about spectroscopy, in order to find out what these objects were made out of and how they're powered. And here the focus was on some of the most distant objects discovered, such as the ones that used to be record holders. These objects existed just under 300 million years following the Big Bang. And they also wanted to check the shape of these objects based on the pictures we have, because if these were spherical and very small, this would actually be more consistent with a dark matter star than any other explanation. But the most important part of the study was trying to compare this to computer models that predict dark stars, and then seeing if the real observations seem to match. And while intriguingly, one of the first discoveries was two new objects. GSGS Z14 and Z14-1 seem to have light signatures that, surprisingly, match the predictions. As a matter of fact, GSGS Z14-0 seems to be the farthest bright object with a very clear light fingerprint that could be used to assess exactly what this is. And even though the object appeared as a tiny dot in some of the initial observations, its actual morphology or its shape seemed to actually match the prediction for dark stars or dark matter stars surrounded by a cloud of gas that's extremely hot. And it was also very massive, at least 1 million solar masses in mass, with some of the other objects matching these observations as well and producing very similar emissions. But here we had some other explanations without dark matter stars, so these observations were not enough. We still needed to have some kind of a signal that would be a definitive proof that this is dark stars. And well, it turns out that one of these observations did have something very unique, a very specific dip at a certain frequency, or a wavelength of 640 angstrom. This is known as the helium-2 absorption line. And intriguingly, this particular line has been predicted in various models involving dark matter stars. But this dip should not exist if this is just a galaxy or a star cluster. Although right now this observation and this dip is not super clear. We need to have additional powerful observations to establish if it's really there, and we definitely need more evidence from other objects, because right now this is relatively weak. Nevertheless, this is an exciting new evidence. However, there's also a major problem, and the problem comes from the observations based on a slightly different dip. Here, by using a different telescope, in this case ALMA, researchers also revealed a very specific oxygen line with a wavelength of 88 micrometers. And this oxygen line, if it exists, might be a problem, because here it would suggest that this object contains oxygen. And in order to contain any heavier elements, we need to have supernova, which would imply that this object contains stars that have gone supernova in the past. Or it would imply that this is not just made out of hydrogen and helium, or that this is not a dark matter star at all, because dark matter stars should form completely by themselves and basically only contain hydrogen, helium, and just a tiny bits of lithium. And so if here we have both the helium dip and the oxygen signal, it would mean that this is maybe something even more complex. Not just some kind of a simple dark matter star, but possibly something even more complicated and something even more bizarre. Something that contains signs of dark matter annihilation, but also signs of potential supernova. Or maybe this is basically just what early galaxies were like. They were just so different and so unique that we cannot explain them yet, which actually has been the main explanation from some of the previous studies. And so until we get more observations and clear signs of certain elements, at least for now, this is still a very hypothetical idea for the existence of dark matter stars. And it will probably take tens or even hundreds of new observations to essentially confirm exactly what this is. And so even though the helium-2 absorption is definitely super exciting, and currently doesn't make a lot of sense, at the moment we cannot definitively say what these objects are. And we can only assume that this is maybe very strange early galactic objects. But with time, and possibly in the next few years, I'm sure someone is going to figure this out. And until then, check out some of the previous videos on similar topics in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon, where you can actually find a lot of additional footage, videos you might have not seen before, and videos without any ads, or consider supporting this channel through the channel membership, where you can find even more footage. Or maybe support this channel by buying the Wonderful Person t-shirt. Either way, stay wonderful, I'll see you tomorrow, and as always, bye bye.
How fast things changed. 2 years ago, when we talked about distant galaxies, most of what we said came with a giant asterisk. We thought we saw the first stars forming. We believed we had an idea of what early galaxies looked like. And when it came to alien planets, we were basically guessing, tracing shadows and hoping for the best. Then James Webb opened its eyes. And suddenly, the asterisks started disappearing. We weren't just detecting planets anymore. We were finding actual signs of what might be in their atmospheres. We weren't squinting at blurry dots from 13 billion years ago. We were looking at fully formed galaxies that, according to everything we thought we knew, shouldn't have even existed yet. And that was just in the first few months. Since then, James Webb has rewritten our understanding of the universe, one target at a time. From ghost galaxies that stopped forming stars billions of years before they were supposed to chemicals in exoplanet skies that don't belong there. If you were hoping for a telescope that would quietly confirm what we already believed. This isn't it. So let's look back, not at the launch, belong there. If you were hoping for a telescope that would quietly confirm what we already believed. This isn't it. So let's look back, not at the launch, not at the hype, but at the work, the timeline, the things it actually found, moment by moment, because the real story of Webb isn't in its design, it's in the discoveries, and some of them still don't make sense. We all saw the image and it looked like a starry wallpaper, nothing more than a tiny dot in the sky, magnified 100 times over. But once the shock wore off, and people stopped saying pretty, the scientists started digging into the details. And that's when things got interesting. That single image, just one, showed thousands of galaxies, not stars, not planets, galaxies. Each one filled with billions of stars of its own, scattered across an area of sky the size of a grain of sand held at arm's length. It was called SMACS 0723, a massive galaxy cluster located about 4.6 billion light-years away in the constellation Volans. But honestly, the name didn't matter. What mattered was what it proved. For the first time, we had a clear infrared look into the deep universe. And it didn't just show distant galaxies. It showed warped light, lensed arcs, ghostly shapes stretched across space and time. That warping wasn't an error. It was gravity. Massive clusters in the foreground were bending the light of even more distant galaxies behind them. And those distortions weren't just beautiful, they were useful. Gravitational lensing acts like a natural telescope. It magnifies, it reveals, it lets us peek behind the curtain. So, in that first image, we were already looking at galaxies that existed over 13 billion years ago. Just a few 100 million years after the Big Bang. That alone was impressive. But here's the part that caught everyone off guard. Some of those galaxies looked too bright, too structured, too evolved. And that didn't line up. According to most models, galaxies back then were supposed to be small, chaotic, and still forming their first stars. But what Webb showed, even in that first photo, was something that looked much further along. Smooth structures, defined clusters, evidence of star formation that should have taken hundreds of millions of years more than the universe had given them at that point. So naturally, the questions started piling up. Were these galaxies forming faster than we thought possible? Were our models of the early universe just wrong? Or were we looking at something else entirely, a different kind of structure, built under different rules? And this was just day one. Before Webb had even locked in its full calibration, before its instruments had been tested across the board, it had already sent us back to the drawing board. Not because the data was unclear, but because it was too clear. It didn't confirm our expectations. It challenged them. What's wild is that this wasn't some deep survey that took months to complete. It was a snapshot, a glimpse, proof that even in the blankest parts of the sky, there are entire universes hidden in the dark, waiting, quiet, until the right lens came along. That lens was James Webb, and in just a few hours it rewrote our map of the early cosmos. A telescope like Webb wasn't built just to stare into the ancient past. It was also designed to look closer. Not at galaxies billions of light years away, but at stars just down the street, orbiting their own little worlds. Worlds we've been chasing for years, guessing their shapes, estimating their temperatures, watching their shadows. And up until now, that's all we really had. Shadows. When a planet passed in front of its star, we'd see a tiny dip in light. That's how we found them. That's how we measured them. It worked, but it was limited. You can learn a lot from a silhouette, but it doesn't tell you what the planet is. It doesn't tell you what it's made of, or what's in its sky, or if anything's living there. Webb changed that. Its infrared sensitivity made it possible, for the first time, to read the actual chemical fingerprints of an exoplanet's atmosphere. Not indirectly, not through noise and modeling, but directly, by splitting the light that passed through it and analyzing the spectrum, one wavelength at a time. That's how we got the first clear detection of carbon dioxide on a planet outside our solar system, WASP-39b, a hot gas giant 700 light-years away. That one single result proved the concept. It wasn't just hype anymore. Webb could read alien atmospheres. And then it went further. Webb found water vapor on WASP-18b, WASP-80b, and GJ-486b. These aren't friendly planets. One's boiling. One's practically hugging its star. But the point isn't that they could host life. The point is that we could read them. Measure the thickness of their clouds, track changes in pressure, see signs of things like methane and sulfur dioxide, gases that mean something when they show up in the right combinations. Then came WASP-17b, and that's where it got weird. Webb didn't just find vapor or gas, it found solid particles in the planet's sky. Tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water droplets, this planet was flinging microscopic quartz around like hail. It was the first time we'd seen anything like that. And it made us realize something. Exoplanets don't follow Earth's playbook. Their weather systems, their skies, their entire logic might be different. Wildly different. And Webb was the first tool that could actually show us. But it didn't stop with exoplanets. Webb turned its gaze inward too, toward our own solar system. And even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune in over 30 years. Not just the rings, but the thermal profile, the pole, the cloud tops. The level of detail was unreal. Then it locked onto Chariklo, a strange asteroid with its own tiny ring system, and detected water ice. That's an object only a few hundred kilometers wide, yet Webb could map its surface. Then it turned to Europa, one of Jupiter's moons, and detected plumes of water vapor venting into space. That confirmed what we suspected from older missions like Galileo and Hubble. But this time it was crystal clear. Europa wasn't just frozen. It was active, breathing, jetting out the contents of its subsurface ocean like a leaky faucet. And Webb was watching it happen in real time. Even Comet 238P/Reed, a small rock in the asteroid belt, got its spotlight. Webb detected water, but no carbon dioxide, which was weird. Most comets have both. This one didn't. That tells us that maybe this comet formed in a warmer region than we thought, or that its CO2 has long since escaped. Either way, that's a clue. About comet formation, about solar system chemistry, about how water made its way here in the first place. And then there were the trans-Neptunian objects, icy bodies way out past Pluto. Webb started picking up traces of methanol and organic compounds on them too, helping us piece together what the outer solar system was like in its earliest days. These weren't just static leftovers. They had chemistry, change, history. So yes, James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, whether it was a planet we'd already discovered or a moon we'd been circling for decades, it showed us something we missed. In 2023, JWST started pouring in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies it was picking up in the first few 100 million years after the Big Bang. Not just faint blobs of light, not background noise. Fully formed galaxies, dozens, then hundreds, in places we thought was still empty space, and some of them were just wrong. Take CEERS 93316, for example. Based on its redshift, it looked like this galaxy existed just 235 million years after the Big Bang, the farthest galaxy ever observed at that point. That's way earlier than we expected anything that complex to exist, and it wasn't alone. Webb kept picking up more like it. Bright, compact, well-structured galaxies that didn't look like they were still forming, they looked done. And that was a problem. Because to make a galaxy like that, you need time. You need heavy elements. You need stars that live and die and explode and recycle their guts into the next generation. You need dust and gas and rotation and gravity all working in sync over hundreds of millions of years. But these galaxies didn't have that kind of time. So, something wasn't adding up. Were these galaxies somehow forming faster than anything we'd ever seen? Were they forming differently, skipping steps we thought were necessary? Or was our whole timeline for the early universe off by a wide margin? And then Webb found something even stranger. The JWST Advanced Deep Extragalactic Survey, JADES, one of its largest deep field imaging programs, focusing on the GOODS S and GOODS N fields, offered detailed images of galaxies at high redshifts. These observations were expected to refine our understanding of galaxy formation and clarify how supermassive black holes achieved their enormous masses so early in cosmic history. However, a surprising discovery from JD's data has challenged fundamental assumptions about the universe's structure, specifically the principle of isotropy, which posits that the universe should appear roughly the same in all directions, with no preferred orientation or spin. In a study led by Leo Shamir of Kansas State University, researchers analyzed 263 spiral galaxies in the GOODS South field using the GANalyzer algorithm, which assesses galaxy spin direction from radial intensity plots. The results revealed a striking asymmetry. 158 galaxies, 60%, rotated clockwise, while 105, 40%, rotated counterclockwise. This imbalance hints at a possible preferred spin direction in this region of space, challenging the notion of a directionless, homogeneous universe. Previous studies have noted similar spin asymmetries, with the effect appearing more pronounced at higher redshifts, suggesting a potential primordial structure in the cosmos. Some speculate this could align with physicist Nikodem Popławski's unconventional theory, which proposes our universe formed inside a rotating black hole in a parent universe, possibly imparting a directional spin bias to cosmic structures. However, Shamir's team offers a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion could make galaxies spinning opposite to our perspective, clockwise from Earth, appear slightly brighter due to blue shift, potentially skewing automated classifications. The small sample size of 263 galaxies and the challenges of imaging faint high redshift objects further urge caution. Larger, more diverse datasets from ongoing JWST observations will be crucial to determine whether this asymmetry reflects a true cosmic phenomenon or an observational artifact. Compounding these challenges to cosmological models, JD's has also uncovered galaxies with redshifts exceeding 13, meaning they existed when the universe was less than 330 million years old. These galaxies, far from being weak protostructures, are luminous, compact, and surprisingly mature. A standout example, JD's GSZ 13-0, with its extreme redshift, has forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such a short time frame. Typically, such collapses require extended periods. Yet these galaxies appear fully formed within the universe's first 300 million years. This is not an isolated anomaly, but part of a pattern. These early galaxies weren't just existing, they were thriving, actively forming stars at ridiculous rates. More stars than they should have been able to form with the limited ingredients available. It was like watching a campfire suddenly erupt into a 5-alarm blaze, but in the vacuum of space, before the wood had even dried. Some astronomers started calling it the too early, too big problem. The galaxies were too massive, too luminous, too soon. So, what's going on? One possibility is that star formation in the early universe was simply more efficient than we thought. Maybe conditions back then, higher densities, more frequent collisions, allowed galaxies to grow at warp speed. Or maybe our models are missing some critical ingredient, a cooling mechanism, a gravitational effect, something we haven't accounted for yet. Another idea is that these galaxies formed from direct collapse. Instead of slowly gathering stars and building up mass, maybe some of them collapsed almost instantly from dense gas clouds, forming stars and black holes in one quick chaotic event. If that's true, it could explain how some of the earliest quasars, the super bright beacons powered by black holes, came to exist so early too. But here's the twist. The more we try to explain it, the more complicated it gets. Because every time Webb stares into those early epochs, it finds more galaxies, not fewer. More light, not less. More structure when we expected randomness. And now, astronomers are facing a deeper question. What if the early universe was never as quiet as we thought? What if everything, stars, galaxies, black holes, came online faster and louder than we've ever imagined? If that's true, then the universe isn't just older than we thought. It's busier, more aggressive, more alive, even in its infancy. And all of these findings that broke our timeline, they came from just the first year of Webb's deep fieldwork. We're only scratching the surface. The moment we found galaxies that were too big for their age, another question came up right behind it. If these galaxies are already so massive this early, where are the black holes that should have grown with them? That's been a long-standing puzzle in astronomy. We know most large galaxies today have a supermassive black hole at the center, sometimes billions of times heavier than our Sun. But we still don't know exactly how they form. Do they start as small ones that slowly eat their way up? Or do some just appear fully grown? James Webb didn't solve that question, but it gave us something we didn't expect, proof that these monsters were already around in the early universe. One of the biggest surprises came from a galaxy called CEERS 1019. It's distant, faint, but when Webb looked closer, it saw a clear signal, the telltale signature of an active galactic nucleus, meaning there's a black hole in the center and it's feeding, not just existing, not just waiting, feeding. That's important because CEERS 1019 isn't in the modern universe. It's from a time when the cosmos was only about 570 million years old. So, how did a black hole, even a small one, form, grow, and start actively pulling in matter that early? That's not supposed to happen. Black holes need material. They need mass to form. They need stars to die. They need galaxies to evolve. And all of that takes time. But this one, and a few others like it, seem to skip that timeline entirely. They're just there. That led researchers to revisit a controversial idea: direct collapse black holes. The idea is that instead of forming from stars, some black holes might form straight from massive clouds of gas, collapsing under their own weight before a single star ever shines. It's messy, it's fast, but it might explain how black holes could have been born big. And once they're big, they don't stay quiet. That's where quasars come in. Webb began spotting quasars, incredibly bright beacons powered by black holes gobbling up matter, from more than 13 billion light-years away. One of them, in a galaxy called J0439 plus 1634, had light so distorted and amplified that it could only be explained by gravitational lensing, a giant galaxy cluster bending the path of its light across space. That's not just a pretty trick, it's a window into the deep past. Lensing takes objects that would normally be too faint and stretches them out, magnifies them, gives us access to more detail than we should be able to get. And it works both ways. One of the most striking examples came in September 2023, when astronomers spotted a supernova, a dying star, that had been triply lensed by a galaxy cluster. It was nicknamed SNH0P. It appeared in 3 places at once, all slightly offset in time. Think of it like a cosmic time delay, the same explosion playing back through different routes in space. That's more than just fascinating, it's useful. By measuring how long each image takes to appear, astronomers can actually use lensed supernovae to measure the expansion rate of the universe, something we've been arguing about for years. There's a whole debate called the Hubble tension, the idea that our 2 best ways of measuring the universe's expansion rate give different answers. But lensed supernovae like SNH0P, they offer a third way, and Webb's sensitivity makes it possible to catch them early, even when they're faint. So, while it's out there spotting galaxies and black holes that shouldn't exist yet, it's also quietly helping to solve, or complicate, one of the biggest cosmological arguments we have. But then Webb found something even stranger. It started seeing galaxies that were no longer forming stars, not millions of years into the universe's history, but within the first billion years. These weren't galaxies that were just starting to wake up. They were already quiet, done. As if they'd been lit up briefly, burned fast, and then just stopped. That's not supposed to happen either. Galaxies are expected to go through a long, messy adolescence. Stars forming, dust flying, chaos all around. But these galaxies, found just 700 million years after the Big Bang, were already quiescent. That's the technical term. No new stars forming, no gas left to work with. It's like finding an elderly person in a kindergarten classroom. You don't expect to see someone that evolved that early. But Webb found them, multiple times. They're now being called Sleeping Beauty galaxies. Catchy name, strange reality, because we still don't know why they stop so early, or if they might wake up again. But it's clear that star formation, just like galaxy growth and black hole birth, doesn't follow one simple rulebook. For a while, Webb's discoveries were all about what we didn't expect. Galaxies too soon, black holes too big, stars forming too fast. But in early 2025, something changed. The conversation shifted from structure and timing to life. The target was K218b, a planet about 120 light-years away, orbiting a cool dwarf star in the constellation Leo. We'd known about it for a few years. Other telescopes had picked up hints that it might have water vapor in its atmosphere. That alone made it interesting. Not Earth-like, but still in what's loosely called the habitable zone. Not too hot, not too cold, just maybe right. But Webb saw something more. In April 2025, scientists announced they had detected dimethyl sulfide, or DMS, in the planet's atmosphere. On Earth, this molecule is only produced by life, specifically by marine plankton. No volcanoes, no lightning, no chemistry we know of makes it without biology. However, scientists caution that unknown abiotic processes, e.g. photochemical reactions in hydrogen-rich atmospheres, could potentially produce DMS. Now, it's important to be cautious here. This isn't confirmation of aliens. It's not proof of anything. The signal isn't strong enough yet to be called a detection beyond all doubt. But the odds? They're high enough to pay attention. Some estimates put the confidence around 99.7%. Not certainty, but not noise either. Webb didn't just pick up DMS. It also spotted methane, carbon dioxide, and hints of dimethyl disulfide. All molecules that in the right mix could point toward biological processes. And K2-18b isn't a gas giant. It's what we call a Hycean world, somewhere between a super-Earth and a mini-Neptune. A water-rich planet with a thick atmosphere, possibly with a global ocean under clouds. That combination, water, methane, CO2, and DMS, is strange. Not impossible in theory, but very unlikely without something living in the mix. Of course, people debated. They still are. Could photochemistry do this? Could there be some exotic process we don't understand yet? Possibly, but that's what makes the observation important. It raises a real testable question. And it's the first time we've ever had that from a planet outside our solar system. No artist's impression, no theory, just data. And while the headlines ran with it, sign of life? The real value is quieter. Webb is finally giving us what we need. Clues, not stories. Signals, not speculation. But that wasn't the only milestone Webb crossed. In May 2025, astronomers confirmed the detection of the most distant galaxy ever seen, a compact, bright object named MOM-Z14. Its redshift was calculated at Z approximately 14.44, meaning the light left it over 13.5 billion years ago, when the universe was just 280 million years old. Let that sink in. We're now looking at galaxies that existed when the cosmos was less than 2% of its current age. MOM-Z14 isn't a massive system like the Milky Way. It's small, intense, bursting with star formation. But it's real, and it's not alone. Webb's deep field work has identified dozens of similar candidates, slowly filling in the blanks of a time we've never truly seen before. Then came one of the strangest visual surprises in recent memory. In July 2025, the James Webb Space Telescope captured an extraordinary image of two galaxies caught mid-collision, forming a system dubbed the Infinity Galaxy. When processed and sharpened, the combined shape resembled a near-perfect infinity symbol, a figure-8 twist of stars, gas, and gravity. Astronomers were captivated by its striking appearance, but the real story lay deeper. Now, yes, the shape got attention, it's striking, but the real story wasn't the symbol, it was what was hiding inside. At the heart of the collision between the two galactic nuclei, researchers identified a supermassive black hole, actively feeding, pulling in material, and building mass. Based on its brightness, energy output, and the extreme gas density of the collision, there's a compelling possibility that this is a direct collapse black hole, a rare phenomenon where a massive gas cloud collapses directly into a black hole without forming stars. This could be a critical clue to one of astrophysics' biggest mysteries: how supermassive black holes grow from nothing to giants in a relatively short time. The Infinity Galaxy, observed about 7.5 billion years ago when the universe was roughly 6.3 billion years old, isn't from the earliest cosmic epochs, but it offers a vivid snapshot of the chaotic mergers that shape galaxies and their central black holes. More than a stunning image, it serves as a laboratory for studying the processes that drive the formation of the universe's most massive objects, illuminating how collisions and extreme environments can spark the rapid growth of black holes. We've been detecting exoplanets for nearly 3 decades now. And in all that time, we've mostly done it by inference, watching how starlight dims, shifts, or gets distorted by something passing in front of it. It's effective, but it's never really felt like seeing a planet. It's more like watching a shadow dance and trying to guess what cast it. So, when the James Webb Space Telescope captured its first direct image of an exoplanet, it wasn't just a milestone. It was a moment of clarity. It happened in September 2022. The planet, Ship 65426b, hadn't even been the focus of any headlines before. One of the quieter targets, orbiting a faint star about 350 light-years away. Not Earth-like, not habitable, just a massive gas giant several times the mass of Jupiter. The kind of planet that's easier to image because it's big, bright in the infrared, and sits far enough from its star to not be drowned in glare. But that's exactly what made it the perfect test case. Using its coronagraph, a device designed to block out a star's blinding light, Webb was able to isolate the faint glow of the planet itself. Not a shadow, not a spectral trace. Actual light coming from the planet's atmosphere, captured and analyzed in detail. That light revealed temperature, cloud composition, molecular fingerprints. It confirmed methane, detected water vapor, even suggested deeper structures in the cloud layers, things like pressure systems and haze. And for the first time, scientists could study a planet in another solar system, as a world with its own visible character, not just a line on a graph. Of course, this kind of direct imaging isn't new in theory. A few ground-based telescopes have managed to do it under very specific conditions. But those images were faint, noisy, barely enough to tell you what you were looking at. This one was different. This was clean, high resolution, detailed enough to break down what the atmosphere was doing, not just what it contained. It was the first time the distant glow of a world outside our solar system could be treated like real data, not a suggestion. And now that Webb has proven it can do that, the possibilities just opened up. Planets like HR 8799c, Beta Pictoris b, and eventually the smaller, cooler ones, the ones we really want to understand, are now within reach. Slowly, carefully, but for the first time, visibly. And again, this wasn't hype. There was no big countdown, no splashy press event. The data was released through peer-reviewed studies, and the image, while simple, carried all the weight of 2 decades of engineering behind it. This is how major progress happens now. Quiet, technical, measured, but undeniable. And while Webb was doing that, it also turned its attention to things much closer, things flying through our own neighborhood, like asteroid 2024 YR4. This was a near-Earth object about the size of a 15-story building, not a headline grabber, not a threat, but still worth studying, because small, fast-moving asteroids are hard to observe with traditional telescopes. They move quickly, reflect very little light, and often slip past with only a brief window of visibility. But Webb caught it, tracked it, measured the surface composition, determined its exact orbital characteristics. It even helped refine the risk models for the Moon, which had a low probability impact window due to gravitational interactions. It wasn't flashy, but it mattered, because it showed that JWST isn't just good at looking into the past, it's good at looking around, at scanning the space near us with more detail than any telescope has ever had, even when the object is small, dim, and moving fast. And that's part of the real story here. Everyone thinks of Webb as the deep universe machine, and it is. But its infrared sensitivity, precision tracking, and spectral resolution have made it useful for everything from icy moons to dusty comets to active asteroids and beyond. It's not a one-trick telescope, it's a toolbox. And the things it's helping answer, from atmospheric chemistry to orbital dynamics, aren't separate. They're connected. Because if we want to understand how common Earth-like worlds might be, or how life could survive in harsh conditions, or what early planets even looked like, we need all of it. Not just the distant galaxies, not just the biosignatures, but the full picture, from here to the edge of what we can see. By now, it's obvious that James Webb isn't just another space telescope. It's not a sequel to Hubble. It's not a mirror in the sky that happens to see a bit further. It's something else entirely. Something that's quietly reshaping how we understand the universe. Not by screaming headlines or dramatic discoveries, but by collecting the kind of data that changes everything over time. That change isn't always loud. Most of the time, it's just a shift in what questions we're even allowed to ask now. Before Webb, we had guesses about the early universe. Now we have measurements. Before Webb, we could detect an exoplanet. Now we can describe its weather. Before Webb, we thought galaxies took their time. Now we've seen them form, burn out, and fade, all within the first billion years. And that's the shift. Not just in what we know, but in how we think about what's possible. Because what this telescope has shown over and over is that the universe didn't evolve slowly and predictably. It evolved fast, and sometimes violently. Galaxies grew faster than we thought they could. Black holes didn't wait their turn. Stars formed, burned out, and passed the torch long before we were supposed to be able to see them. And yet, there they are, clear as day, sitting in Webb's data. So now we're left in an unusual place. A place where some of the biggest answers have raised even bigger questions. Why were so many galaxies already mature when they shouldn't have had time? How did black holes appear so early, and what made them feed so fast? What kind of worlds are out there that could carry not just water and clouds, but chemicals we've only ever seen here on Earth? And, maybe the most honest question of all, how much of our understanding was built on models that were just too neat, too slow, too simplified? Webb isn't here to confirm what we thought. It's here to challenge it, to test it, to make sure we're not just building stories that feel right, but ones that match what's actually out there. And it's still early. There are thousands of observations in the pipeline that haven't even been made public yet. Entire surveys that will run for years. Missions planned to pair Webb's results with new instruments, ones that'll look in other wavelengths or catch up in resolution. And then there are the things we haven't even imagined yet. The surprises, the quiet anomalies, the strange patterns in background galaxies, the leftover questions from redshift measurements that don't quite align, the weird atmospheres, the gaps in stellar mass, the lensed flashes that might be something more. Because the thing about a telescope like this is, you never really know what matters until you look. And when you finally do, it's never what you expect. No one knew Webb would find galaxies that shut down before they even got started. No one guessed we'd get hints of life from a planet 120 light-years away this soon. No one expected such clear detail, from the furthest galaxy ever seen to the clouds on a gas giant right next door. But that's what it's doing. Not once, not occasionally, but constantly. And in doing that, Webb has quietly shifted astronomy from a field based on hopeful estimation to one grounded in evidence, detail, and sometimes uncomfortable clarity. It's not about pretty pictures. It's about finally seeing what's real. And if this is what the first 3 years look like, the next decade isn't just exciting, it's going to change everything.
This scumbag TikToker just filmed himself stealing from graves in Japan for attention online, which ended up upsetting an entire country before his career has really started. This is Lockie Jones, an Australian YouTuber who believes that kindness is key, and judging from his actions, I don't believe he actually thinks so. But he's currently making headlines because he recently decided to visit Japan. He filmed himself committing some crimes, and then he's responded to those crimes in the dumbest ways possible. Behavior that we've honestly seen quite a few times before here on this channel, but let's get into it. I guess you could say if only Lockie Jones was paying attention for the past few years, as this stuff just does not fly anymore over there. And at this point, it's sad to say, it's not even original anymore. We've had Johnny Somali completely disrespect Japan and South Korea for a while now, and now you have Lockie Jones visiting a grave in a controversial area in Japan and literally stealing offerings left for family members of the deceased. So, I mean, this is just desperate and extremely cringeworthy behavior, but to understand how he even got here first, we need a brief recap of who this scumbag is and how he even got here. So, around 3 years ago, Lockie started posting content on his TikTok, Instagram, and YouTube account. First impression of the guy, he doesn't seem the brightest due to posting clips like this, just asking the first guy he finds that's not white where the local kebab store is.
Amigo, we look for the kebab store. You know what I mean? We're hungry. Look at him.
Why would you post this? And maybe more importantly, why would you leave this up? But it does feel like he has a little bit of an obsession with law enforcement, because there's multiple videos after this of just him filming and mocking police officers in Peru.
Hey, gang, gang. Woo!
That's the biggest gang in Cusco, the Policia.
Then you have him making crypto investment advice, because everyone wants crypto advice from a dude with no direction in life.
You need to have a bag of Solana. It's big, it's growing. And the American government just listed it on their list of crypto assets that they will be investing in. You can stake Solana at above 6%. If you just buy it right now and forget about it, let's do some numbers, because this thing is hitting $1,000 for sure.
Meanwhile, the rest of his clips just featured clips of his travels from his series called Idiot Van Diaries.
All right, update on the Van Diaries. We have a stowaway. Hold up. Can you
That he's going to randomly flash in when I cannot gap close.
Selfish.
Okay, listen. Poo.
Okay.
Poo.
I don't want to
listen.
talk.
Wait, last thing. My Galio can help me push out the soldiers here. He decides instead that when Set is having all of his cooldowns up, that he's going to randomly flash in when I cannot gap close. What the fuck is this? No ping, nothing. Bro, like, you're laughing because you know I'm right. What the fuck is this shit, bro?
It's full of
crazy.
Galio's fault. You wanna talk to me? That is full of Galio's fault.
I mean, bro, no ping, nothing. He just fucking full sends his flash like this. Are we serious? Just fucking full sends his flash like this. Are we serious?
I think it's hard.
And then
really
you
hard
told me
to
the
talk to
entire.
you.
Yeah, because why? Because you're not telling me that my mom's dead. Are we serious?
I think it's hard.
And then
really
you
hard
told me
to
the
talk
entire.
to you.
Yeah, because why? Because you're not telling me that my mom's dead.
You
kept calling me bad dog, and now my mom's dead.
Me.
What? Oh, did you forget?
You want me to recognize Galio's fault.
Yes.
I know Galio has fault, but not full of his fault.
Okay, so what's my fault then?
I don't think if Galio not helped you, you can clear all the soldiers.
Okay.
And you will not die.
Pooh, can I ask you a question? Can I ask you a question?
Yes, go.
Okay. When Galio comes here, okay? And he helps me clear the soldiers, okay?
Yes, why?
This is good.
Yes, this is a good soup.
Yeah, this is good.
if he helped you to
But
clear the
this
soldier,
is
this
fucking.
is
Do you
oh
agree?
yes, but it I can I say this?
Go.
Was he has duty to help you to clear the soldier?
I mean, no, but he decided to.
He has no duty.
Okay, Pooh, can I ask you a question?
Yes.
Okay, let me ask you a question. Do you have a
Yes.
brother or a sister?
Yes, I have a sister.
You have a sister. Okay. Imagine you and your sister, you go for a walk. Okay? I'm asking, okay? You guys are on walk, you're going to the bakery. Okay?
Okay.
A police
Okay, good.
officer,
Okay,
okay?
good.
He sees
Okay.
robber stealing old woman purse. Okay?
Okay.
Okay. Police
Robbers
officer.
stealing.
Yep. So robber stealing, okay? Police officer, he sees this, okay?
Yes.
Police officer whips out gun. Gun police officer. Bang, bang, bang. Does not kill robber, kills your sister. Would you get mad that your sister is dead because the cop wanted to do a good thing? Yes or no?
Oh, you wanna say we are a team. Galileo has duty to help you to clear the soldier.
No. I'm not saying he has a duty to do anything. I'm saying that what he did was good, and then it was horrible for no reason.
Okay, that made me 1/10.
It made you what?
Is that? Made you 1/10.
Look at my game. Okay, are you looking at my game? I don't feed, right? And then here, you, right?
What?
You see this, and you know what you type?
Yes, I
You
saw that.
you type
I saw that.
you type noob mid bad dog mom die. That's what you type, and you clear chickens. Buck buck
Yes.
buck buck. Go bye bye. And
Yes.
after that, me, my asshole. Ah! And you're killing the buck box. Why?
What? Why I killing the bird, the chicken?
Yes,
Oh, what should I do?
you should counter the dive.
I should standing. I should standing. Stick to you.
Yes,
Stick to you.
or just sit here.
Yes, I should standing. Stick to you. But you ignored my sign.
Your sign was telling me that I should myself and that I'm a bad dog and that my mom is dead. What sign, bro?
That depends on at the game beginning.
Dude.
You standing here.
Dude.
You standing here, and you ignored my sign.
Dude. So you're saying
that depends on at the game beginning.
Dude.
You standing here.
Dude.
You standing here, and you ignored my sign.
Dude. So you're saying you let me die because I didn't ward your raptors?
Yes, I let you die. That was not my fault. I have no duty to stick with you. Waste of my time. Because I think you 2v1 got killed. Why I should help you?
Because
Why?
you would get a free kill.
Because I have a sister? Because I have a sister?
Dude.
Robbers were stealing? Because of this? I should have a gun? I should play grapes?
Bro.
Good. No, what going on?
Bro, if you have no duty to help me, then I will go 0-10 and we will lose. So you should not be flaming, bro.
I didn't help you, so we lose.
Yes.
But But was this drug help their meat? Is that funny? Is that funny?
Okay, you know what it's like, bro? Can I give you an
Is that
analogy?
funny?
Okay, no, let me
Wha-
tell you something.
Why
Let me
I should waste my time to
Okay.
stick with you?
It's like imagine, right? K-pop billionaire, billions of dollars, getting mad that the government gives money to homeless veteran with no arms, no legs, but they don't give money to him. Do you know what I mean?
No,
Okay,
no.
what I'm saying
I don't know government.
in this position, you can help. I know that I didn't help you early, but the point is to win. You cannot hold grudges, bro.
You wanna talk to me if I can stick with you. This game You wanna talk to me if I can stick with you. This game would be win. Is
Ye-
that
yes?
be win? Is
Ye-
that?
yes?
Oh, bruh. I think why you can't. Why you can't give me an ice stone at the beginning? I signed you many times. Why you can't give me an ice stone at the beginning? I signed you many times. Why?
Dude,
Why? Why you are laughing?
dude, how the
I,
dude?
why? Why you are laughing?
Dude, how the fuck
Same
are we
question.
still on the warning
I think this is the same
totem?
question. You think I should stick with you to protect you. I should stick with you to protect you. But
Dude.
you never helped me. You ignored
Okay,
me. Why I
okay,
should help you?
okay, wait, let me ask you a question. Let me ask you a question, okay? Do you love
I don't-
your mom?
I don't want to reply you.
No, let me ask. Do you love your
bruh.
mom?
No,
Yes
bruh.
or no, you don't love your mom?
No,
You don't like
bro.
your mom.
I think we have nothing to say.
Bro, no,
You
what
think it was Galio's fault? You think I should help you?
I'm saying
That's
you
enough.
could have.
That was my fault and Galio's fault. You have no fault. He was a good me.
Dude,
Yeah.
I'm saying you could have helped me, bro. And you sit here and you're like, no ice thong, I ain't. And then you tell me my mom dead, bro. Like, you could be helping me, but instead you tell me no ice thong, mom dead. Seriously, dude. He left. It's like he left and he unadded me. It's like he blocked me on League. Oh my god. Wow. That guy wasn't even Korean, he was Chinese. Wait, how do you know? It's mostly Chinese people that use the mom dad insult? Oh, really? Okay. He also called you Korean. He said you Korean, guys. Korean players never their fault. I honestly think that was the highlight of the Korea trip. The ice stone guy.
Vamos?
The vibe I get from this guy is that he might be having an early midlife crisis, because just from reading his Instagram bio, it says stuff like reality warper. And on his YouTube about section, it also says that I'm exploring the esoteric truths behind the facade, and let's find out how to achieve your ultimate elite timeline. You know, because his timeline is looking pretty damn elite at this point. I think the best quote I see from him is, "We will attack the dark topics with humor, irreverence, and questioning to ensure that we can shine enough light to bring us through the apex and beyond." Brother, what? And from what I'm about to show you, it more sounds like I'm allowed to be a scumbag because I hide behind a layer of irony and fake truths, but hey, to each their own. And this brings us to his visit to Japan, which started like this.
Tokyo, Japan, Hamura.
Listen, you know, Poppy respawn. Like, Poppy could have actually held this game if she didn't actually just disconnect. Oh.
Rare wine. So
And we are looking for because the mission is, we want to go to the forest and shoot a picture of Logan Paul, and maybe grab a stick off a tree to make a magic wand.
I mean, with that, I feel like it's safe to say this isn't going to be the end of content like this. Influencers like this genuinely believe controversy is going to be their way into stardom, when in reality, you're just going to be featured in some videos where people discuss how much of a terrible person you are, or laugh at you for being a dumbass and doing this. Then in a few months, absolutely nobody would care about you again until you do something extremely outlandish. This is essentially the entire career path that Johnny Smalley had. Honestly, this is just a playbook for how to ruin your life for a little bit of attention online, and it's definitely not worth it. You can ask Vitaly, who's currently still stuck in the Philippines, or Johnny, who's still stuck in South Korea. They're definitely not having a good time right now.
We shoot Logan Paul to defend the honor of the Japanese people. He should not have done a nasty video in a sacred forest.
So it's almost like he's being sarcastic and has this like new age opinion of, oh, it's just a joke, mate. Don't worry, yeah? You're just a little bit of a snowflake, yeah? I will never try to repeat an Australian accent again. I feel like it was teetering more on the British side than anything else, but yeah, let's just move on. The only comedy in this situation is the fact that he's dumb enough to do it. So what did he actually do? Well, in a video titled Force Japan Part 2 Graveyard Flip, we can see Loki approach a graveyard, which we can only assume is just outside of the forest that Logan Paul made very infamous on the internet, and I guess just proceed to take a can that's been left on a grave and chug it, even cheersing the grave about it.
Oh, look at this guy. Full can of Kieran. Should I drink it? Should I drink it? By the way, shout out this guy. Legend, clearly a legend. And missed by his mates. All right, we got the Harry Potter coin. So we go dragon or wizard. Dragon we drink, wizard we think. That's the dragon. All right. That's warm as fuck, shit. Over the shoulder. Good luck. Good luck. Lucky blessings. Rest in peace. And if you went down angry, I hope you get vengeance. Cheers, gobber.
Wow, this guy's so cool. And to give more context, there was a pretty good comment left on his video. In Japan, the offerings to see on the grave aren't decorations or props, especially not for content. Families leave food, drinks, and incense as gifts for the spirits and their loved ones. They're believed to reach the deceased in some form. So essentially he was stealing an offering given to a deceased person, not only disrespecting a culture, but also their family. So you would think maybe he didn't understand what he was doing, and that after receiving some backlash online, he would apologize for that situation, but no, that is definitely not the case.
I'd like to take this video, this lovely day, to apologize to absolutely no one, for everyone who went and yapped about he took a drink from a dead man. Have some concern for the living, yeah?
I think you may have had a few too many graveyard beers before writing this, because what is that even saying? Have some concern for the living? Like, what is the argument here? But I guess let's hear him out.
I see a lot of people out here and they are acting in a way that they would not like to be treated.
Okay, so he's seeing people acting in a way that he wouldn't want to be treated. I'm assuming he's speaking about himself, because I don't think he'd like someone else going to one of his relatives' graves and destroying the flowers left there.
If I was that dead guy, I'm not drinking that drink. What is the problem? The problem is how some of you are thinking is okay to behave just because everyone else is behaving that way.
So instead of apologizing, he's just trying to spin this narrative of act your own way and not follow the norms of society, even though it may upset and anger an entire culture, all while being visibly intoxicated. Or maybe I'm just wrong and he's just incredibly stupid. Or both, who knows? So he then proceeds to jump off a bridge into this massive lake and proceeds to use this as a metaphor for his troubling online existence.
I mean, do you remember the saying? If everyone, what was it? If your friend jumped off a bridge, would you do it? Well, put that saying to the test. Be sane in an insane world is to be crazy.
Okay. Why? But briefly after this, he promotes his Japan YouTube video and describes it as discussing groundbreaking stuff. So I thought I'd take a look, because so far I haven't seen anything groundbreaking from this guy, and that's still the case after watching this video.
At the very least, I wanted to hear the stories of some of the Japanese people, as I have heard from others all over the world. Yet, this is buried under 6 feet of venomous black mess. Soul-sucking technological terror.
Because essentially this whole video has this narrative that suggests that Japan and their culture has completely changed and lost its roots, including that they have a massive PDF file program, he alleges, which is reinforced by the culture and how some of the women dress. This is what he alleges here. But this still begs the question, why does this give you the right to disrespect someone's culture just because you think there's aspects of it that you deem as wrong? And if you truly believe all these things, why is your way of getting attention to the story stealing from a random graveyard? Like, he's just defending his garbage behavior with a whataboutism argument. Like, he just seems to be a fried conspiracy theorist, bro, and he's made it his entire personality.
If your focus was on the right outlets and beliefs, and you had individuals inspiring you, you could have the highest percentage of superheroes from any nation.
Yeah, ladies and gentlemen, I present you Japan's new spiritual leader in collaboration with ChatGPT, because he didn't come up with that himself. And for some reason, he just keeps making these videos almost like he's thinking, well, now I have some attention of Japan, let's drop some facts in them. Like, dude, what are you doing?
Look, if you felt I desecrated your dead, I am sorry. It was a mistake. I'm coming clean. I shouldn't have portrayed that. The reality we are walking through is going through a period of mass psychosis, and it took crazy to get